Now, coming to the plastic deformation of polycrystalline metals. Plastic deformation of polycrystalline metals. Polycrystalline means there are more number of grains. It is not a single grain. So since in a polycrystalline material there are number of grains, the deformation process that takes place in a polycrystalline metal is somewhat different when compared to single crystal. And there are certain other features that are quite different from single crystal because there are no adjacent grains. Due to the presence of the adjacent grains and grain boundaries in the case of a polycrystalline material. So what are the advantages a polycrystalline metal has and what disadvantages a polycrystalline metal have with respect to single crystals, you would be able to answer after the lecture. Now, in a polycrystalline metal, there are number of grains. The boundaries separating the grains are called grain boundaries. The atoms within the grain boundaries, they are highly strained and they are distorted when compared to the atoms within the grains. So the atoms along the grain boundaries or the atoms in the grain boundaries, they are the regions of high energy. So grain boundaries are higher energy when compared to the grains. The reason for this is atoms in the grain boundaries, they are highly strained and disordered, distorted when compared to atoms within the grains, which are orderly arranged. The average diameter of the individual grains within a polycrystalline aggregate, it decides the grain size of that metal. In a polycrystalline metal, you have number of grains. So the average grain size of the grains within the polycrystalline aggregate, it defines that material grain size, finer grain or coarser grain. So that average grain size of the individual grains decides the grain size of the polycrystalline metal, whether coarse grained or fine grained. So these grains, they are a result of solidification process and occur as a result of misorientation of the grains as they are frozen into position. So during solidification process, these grains form and the misorientations between the grains as they are frozen into positions leads to the grain boundaries. If this is the melt, the liquid metal, as the temperature is decrease in temperature, a small nuclei tends to form. Small nuclei forms. This is the nuclei. That is, the solidification starts by the formation of small nuclei. This nuclei further grows into small crystals, individual crystals, as the temperature is decreased, and finally forms into grains and grain boundaries. So this is the formation or solidification process. As the temperature is decreased, the melt forms small nuclei initially, where the crystals grow, and the adjacent crystals, as they grow, as they overlap, they form the grain boundaries. So atoms in the grain boundaries, these are the grain boundaries and these are the grains. So atoms in the grain boundaries, they are highly strained and distorted, and they are not regularly arranged when compared to the atoms within the grains. So a magnified image of this one, that means with respect to the atom arrangement, is when you can take this microstructure, when you take this structure along the grain, this is the grain boundary, atoms within the grains, they are regularly arranged. They are regularly arranged, whereas the atoms in the grain boundaries, they are distorted, strained, and they are less regularly arranged. They are disordered, whereas within the grain, they are regularly arranged. They are regularly arranged. So these grain boundaries, they are of higher energy. Small angle grain boundaries occur when the misorientation between the grains, it is less than 5 degrees. If the misorientation is less, or it is less than 5 degrees, small angle grain boundaries occur. These small angle grain boundaries, they are represented as an array of or row of parallel edge dislocations. So the regions surrounding these small angle grain boundaries are called subgrains or subcrystals, which are free of dislocations. So if the misorientation, it is greater than 5 degrees, it is called low angle grain boundaries, and these low angle grain boundaries, they are represented by an row of parallel edge dislocations. And the regions surrounding these low angle grain boundaries are subcrystals or subgrains, which are free of dislocations. If the misorientation, it is greater than 10 to 15 degrees, then the formation of high angle grain boundaries result, that we have discussed earlier. So low angle grain boundaries are when the misorientation between the grains, it is less than 5 degrees, and moreover they are represented as an array of parallel edge dislocations. So these are called subgrains or subcrystals. If the misorientation is greater than 10 to 15 degrees, then it is called high angle grain boundaries. And as we have discussed that atoms in the grain boundaries or along the grain boundaries, they are not regularly arranged. They have higher energy when compared to the atoms within the grains, because they are less orderly arranged, less regularly arranged, and they are distorted and they are strained. As the grains, they solidify, as the atoms, they solidify, they are frozen into the position. So these grain boundaries are areas of misfit and relatively more open structure. These grain boundaries are the regions for many irregularly placed atoms. The atoms are irregularly placed. They are less orderly arranged, as well as these are the regions for dislocations and voids. All grain boundaries, they act as sink for dislocations and vacancies that can disappear. Grain boundaries, these are also preferential regions for the accumulation and segregation of many types of impurities. Weakening of the grain boundaries or embrittlement at the grain boundaries can also occur due to the preferential phase precipitation that occurs at the grain boundaries, or the reaction of the grain boundaries with the environmental species like hydrogen or oxygen. Thereby weakening or embrittlement also takes place at the grain boundaries due to the reaction with the environmental species or due to the precipitation, preferential precipitation that takes place at the grain boundaries. So these grain boundaries, they are of very higher energy. They tend to decrease their area. They try to decrease, grain boundaries try to decrease their area in order to minimize the internal energy of the system. They try to minimize their area to decrease the internal energy of the system. The main driving force for this is the surface tension. So in order to reduce the energy, this surface, because the main driving force for this is the surface tension. So these boundaries try to straighten out in order to reduce the total internal energy of the system. They try to straighten the irregularly or the more irregularly arranged atoms. They try to straighten out. These are very irregular boundaries, irregular shaped boundaries. So they try to straighten in order to minimize their energy. That means they grow inside, the grains grow and the grain boundaries area decreases as the grain grows. So the grains which has more than 6 boundaries, a grain which has more than 6 boundaries, they are more stable when compared to the grains which has less than 6 boundaries. And these boundaries are planar in the case of stable grain boundaries. So these grain boundaries, they try to minimize their area to reduce the internal energy. So at higher temperatures, at temperatures greater than above 0.5 of the absolute melting point, large mobility of the atoms take place. Grains which have more than 6 boundaries or 6 faces, they try to grow. They try to grow. And the grains which have less than 6 boundaries or 6 faces, they try to shrink and they are consumed by the larger grains. So these grain boundaries, they are of higher energy where many things takes place, like diffusion takes place at the grain boundaries, reaction with the environmental species takes place, and depending upon whether it is coarser or finer grain, the strength of the material also depends. Coarser grain means grain interior is larger when compared to the area of the grain boundary. Grain boundary area is smaller. For the case of fine grain, grain boundary area is more than the grain interior. So the temperature at which both the grain as well as the grain boundary have the same strength, it is known as equicohesive temperature. Above equicohesive temperature, grains have more strength than grain boundaries, and below equicohesive temperature, grain boundaries are stronger than grain interiors. So fine grain material is stronger because of larger grain boundary area below equicohesive temperature and above equicohesive temperature, coarser grain is stronger because grain boundary area is smaller for a coarser grain material. Now, what is the reason for a fine grain material to be stronger when compared to a coarser grain? In the case of plastic deformation, for the case of single crystal which takes place, the plastic deformation that takes place in the single crystal by means of slip, there are no restrictions to the slip. Why? Because there are no adjacent grain boundaries. It is only a single grain. So for the slip to initiate or the slip to take place, it requires a critical stress for slip to start. Whereas in the case of polycrystalline material, there are adjacent grains. So the slip that takes place in a grain, if it has to cross another grain, it has to cross the grain boundary, there are more restrictions. Why? Because due to the presence of these grain boundaries, it cannot normally cross the grain boundary. It has to reverse its direction. It has to change its direction. The slip has to change its direction at the grain boundary. If the grain boundary area is larger, more the changes in direction and more the length, more the deformation path. So this increases the strength of that material. For the case of very fine grain material, grain boundary area is more. More the grain boundary area, the slip has to change its direction if it has to cross the grain boundary. It has to change its direction. So more restrictions to changes in direction, as well as the deformation path is also higher. Thereby more force is required. So this strengthens the material. So this is the reason why finer grain size material is stronger than the coarse grain size material, as well as the ductility of a fine grain size material is also good. Both strength as well as ductility is good for a fine grain size material, because the slip has to change its direction if it has to cross the grain boundary, as well as the deformation path is also greater. And moreover, the dislocations, for the dislocations to move, they have to cross the barriers. The barriers are the grain boundaries, where they get piled up at the barriers. So more force is required for the dislocations to cross the barriers. So these are the main reasons for a polycrystalline material which is stronger than single crystal, as well as a fine grain size material is stronger than coarse grain size material. So this is a figure for the case of polycrystalline material. So in the case of plastic deformation of a single crystal, slip has taken place. So for the case of single crystal loaded in tension, there are no restrictions for the slip. These are the slip planes. There are no restrictions for the slip. The main reason is there are no adjacent grain boundaries. Whereas for the case of polycrystalline metal, when loaded in tension, since it consists of number of grain boundaries, the slip path has to change its direction, and if the grain boundary area is larger, more is the deformation path, more restrictions to the changes in direction. More changes in the direction, as well as the length also is more. So these are the slip lines. So these are the slip lines where the slip, it has to change its direction in the adjacent grain. So more the grain boundary, more the restrictions to change its direction, and deformation path is also more. So this is the main difference between the plastic deformation for a single crystal, which requires a critical stress, and for the case of polycrystalline metal, where there are number of grains and grain boundaries. So the slip has to change its direction if it has to move to adjacent grain, and more the grain boundary area, more is the changes in direction, and more is the length, or the deformation path is more. So for a fine grain size material, the strength and ductility is very high. So this is one of the strengthening mechanisms. So if you want to strengthen a metal, you prefer a fine grain size metal and compared to coarse grain, or give such heat treatments such that a fine grain size metal is obtained. So one more important relationship between the grain diameter and yield strength is given by Hall-Pitch relation, given by two scientists, Hall and Pitch. So that relationship is known as Hall-Pitch relation. Hall-Pitch relation, where it is a relation between yield stress, sigma subscript y indicates yield stress, is equal to sigma I is the friction stress plus K subscript y d to the power of minus half, where d is the grain diameter. So yield stress is inversely proportional to square root of the grain diameter. Finer the grain size, greater is the yield strength, higher is the yield strength. Ky is known as the locking parameter. K subscript y is known as the locking parameter for the dislocations. It is the locking parameter for the dislocations. This has a different value. This is a constant. It has a different value for different metals. So how efficiently a fine grained metal, how efficiently the yield strength can be increased by refining the grain size, it depends upon this locking parameter. Its value is different for different metals. For example, steels, you can achieve higher yield strength in steels by refining grain size, whereas in the case of aluminum alloys, the same cannot be. By refining the grain size, the yield strength of aluminum alloys cannot be increased to a greater extent, whereas this has been to a greater extent in the case of steels. Refining the grain size increases the yield strength to a greater extent, around 200 MPa in the case of steels, 200 plus MPa in the case of steels, whereas for the case of aluminum alloys, it's around 70 MPa. So refining grain size increases the yield strength, depends upon the parameter, that is a locking parameter, which has a different value for different metals. So we have already dealt about the grain boundaries having the number of boundaries or number of grains having the number of boundaries or number of faces. If it is less than 6, it is unstable. If it is more than 6, it is stable. More than 6, the grain boundaries, they try to grow. The grains try to grow at higher temperatures. Whereas if it is less than 6 faces, then they shrink and they are consumed by larger grains. Grains which are having less than 6 faces or 6 boundaries, they are concave inside and they shrink. Whereas grains with more than 6 boundaries or 6 faces, they are planar and they are stable and they grow at the expense of this small grains which are having less number of grain boundaries, that is less than 6 boundaries. So this occurs at temperatures greater than 0.5 of the absolute melting point. Certain second phase particles like the precipitates, dispersoids, second phase particles, they pin down the grain boundaries. That means they do not allow the grain boundaries to coarsen. So they act as the barrier for the grain boundaries to grow. They pin down the grain boundaries. They do not allow the grains to grow. These second phase particles like the precipitates, dispersoids, they do not allow the grain boundaries to grow at higher temperatures. They pin down the grain boundaries. So this is about the grain boundaries. What are the grains and grain boundaries? The misorientations between the grains as they are solidified into position. If the misorientation is greater than 10 to 15, it is called a high angle grain boundary. Less than 5 degrees, it is called low angle grain boundary. And low angle grain boundary can be it is represented as an row of parallel edge dislocations, whereas the region surrounding it, it is known as subcrystals or subgrains, where it is free of dislocations. So these grain boundaries, these high angle grain boundaries, they are the regions of dislocations, they are the regions of voids, they are the regions of large number of largely irregularly placed atoms. They are of not regularly arranged. Atoms are not regularly arranged. They are irregularly arranged, irregularly placed atoms, and they are highly distorted, highly strained. So these are the regions of high energy sites. So they take place active in corrosion process, in diffusion process. And in revealing the microstructure, when you etch the sample, grain boundaries etch more preferentially when compared to the grains, because they are high energy. The reason is mainly due to the less regularly arrangement of atoms. So these grain boundaries acts as a sink for dislocations and vacancies. That means they can disappear at the grain boundaries. Moreover, the weakening or the embrittling occurs. Embrittlement or the weakening of the grain boundaries also occurs due to the preferential precipitation of certain phases, as well as the reaction with the environmental species like hydrogen and oxygen. So in order to pin the grain boundaries at higher temperatures so that they do not coarsen, they do not grow in size, second phase particles are important to pin down the grain boundaries. In order to reduce the total internal energy of the system, these grain boundaries tends to decrease their area by straightening. So the driving force for this is the surface tension. So the grain boundaries and the grains, they have the same strength at a temperature. The temperature is known as equicohesive temperature. Above that temperature, grains are more stronger than grain boundaries, and below equicohesive temperature, grain boundaries are more stronger than the grain interiors. So fine grain size material means larger grain boundary area is stronger below equicohesive temperature, and whereas above equicohesive temperature, coarser grain, that is area of the grain interior, is more when compared to the grain boundary area. Grain boundary areas are smaller for the coarse grain material, that is stronger above equicohesive temperature. So this is about the grain boundaries and grain sizes. So we have already discussed that for a metal to be of either fine grain or coarse grain, it depends upon the average diameter or average grain diameter of the individual grains within the polycrystalline aggregate. So for this, one calculation is there to find out the grain size. The formula to find out the grain size is small n is equal to 2 to the power of capital N minus 1. where capital N is the ASTM grain size. ASTM stands for American Society for Testing of Materials. ASTM grain size number. In the introduction class, we have already discussed that mechanical properties like the hardness, strength, in order to carry out the tests to find out the results, in order to get the mechanical properties like the hardness, strength, ductility, some tests have been carried out. These tests, they are used by number of regulatory agencies. So thereby these tests are to be standardized and then results are to be consistent. So we have different standard agencies. So one of it in United States is ASTM. So capital N stands for ASTM grain size number, and small n is number of grains per square inch. Number of grains per square inch when observed at a magnification of 100x. So this is the formula to find out the number of grains or the grain size of that material per square inch at a magnification of 100x. Small n is the number of grains per square inch and capital N is the ASTM grain size number. And this is the equation valid when observed at a magnification of 100x. So if the magnification is other than 100x, then the equation has to be changed. So this is for 100x magnification, small n is equal to 2 to the power of capital N minus 1. For example, if the ASTM grain size number is given as 5, if capital N ASTM grain size number is 5, the number of grains per square inch can be calculated as small n is equal to 2 to the power of 5 minus 1, that is 2 power 4. So number of grains per square inch at 100x magnification is 2 power 4, that is 16. 16 grains per square inch at 100x magnification of 100. So this is about the grain boundaries, grain boundaries, and the difference between the plastic deformation of a polycrystalline metal and that of the single crystal. So by this, you should be able to differentiate the plastic deformation of a single crystal and that of the polycrystalline metal, and why polycrystalline metals are stronger than single crystal, and why fine grain metal is more stronger than coarse grain. This you should be able to answer. It not only depends on the Hall pitch equation, but you should give a proper reasoning that slip has to change its direction. More the number of boundaries, more the changes in direction, and more is the deformation path which strengthens the material. Moreover, dislocations, the grain boundaries are the obstacles. So more stress is required to overcome the obstacles. So you need to answer these questions. You should be able to answer these questions, the differences between the polycrystalline and the single crystals. And moreover, if you are able to understand the grains, the grain boundaries, in the further topics that we will be able to discuss, fracture, fatigue, creep, which is a high deformation, which is a high temperature process, which occurs at temperatures greater than about 0.5% of the absolute melting point. So there you prefer a coarse grain material, whereas at low to intermediate temperature you prefer a fine grain material. You will be knowing the reasons for this once this concept is understood. Why you prefer a coarse grain material at temperatures greater than 0.5 of the absolute melting point, and why pinning down of grain boundaries is required, why grain boundaries are not allowed to grow certain temperatures, why it is necessary to pin down. So all these things you will be able to understand if you have understood this concept, grain boundaries. why they are of high grain boundaries are very high energy, why they etch more readily than grains, why they take active part in diffusion process. So all this can be easily answered if you have understood this concept of grain boundaries. Twins that I have discussed in the earlier class. Twins also, they are the boundaries. Twin boundaries also we have discussed. But twin boundaries, they are of less energy when compared to grain boundaries. So they etch less readily than grain boundaries. And they are less active than grain boundaries because the energy is less when compared to grain boundaries. Grain boundaries are high energy sites when compared to twins. So these things, the differences, the reasons will be known to you, or you will be able to answer all these things if this concept is clear. If any doubts you have in this concept, in the plastic deformation of single crystals and the polycrystals, that is the grain boundaries, please mail to me or contact me. Do inform me any doubts or further clarifications or any explanation further required, because this is very important. Moreover, in the fracture means this will be discussed in the coming topics, fracture, fatigue, creep and all. But since I am talking about the grain boundaries, grains and grain boundaries, they are the regions for the strengthening mechanism. For the strengthening mechanism, you need a fine grain material for good ductility and for increased strength, for high strength. Yield strength is inversely proportional to the grain diameter. Similarly, fracture resistance is also good for fine grain material. Fracture means separation of a body into two or more parts. If you apply very high amount of stress, when the stress is lower, it undergoes elastic deformation. As soon as the load is removed, the material regains back to its original shape. If the stress is slightly higher, the material undergoes some permanent change. It means it undergoes plastic deformation. For still higher values of stress, the material undergoes fracture. That means fragmentation of this solid into two or more parts, separation into two or more parts. So for fracture to take place, what is the initial thing that happens in the material? Voids form. These voids coalesce to form cracks. These cracks, they propagate under the application of stress and the material separate to two or more parts. So the precursors for the fracture to take place is the cracks. So fine grain size material is more resistant to fracture than a coarse grained material, because the crack size is limited to the grains. So fine grain material is good for fracture resistant. For high strength material, prefer fine grain size material. High yield strength fine grain size material, high strength and ductility fine grain size material. As well as you appreciate a coarse grain material is also preferred for high temperature applications, because above equicohesive temperature, grain boundaries are having less strength than grains. So smaller the grain boundary area means coarse grain size material is preferred. So I hope you have understood this grain boundaries.